from the nonparametric Bayesian world. My last talk, which you might have remembered, was sort of like trying to be a unification of frequent distance Bayesian, but this is just all Bayesian all the time. So I'm really curious about your guys' impression of this and like how it differs in flavor from your sort of work. So yeah, so the title is Nonparametric Bayesian Clustering via Infinite Warped Mixture Models. And I'm really happy being in Duvenaud Lab to have at least one paper with the word infinite in it. I felt like I had to do that before I could really say I did Cambridge. Although Peter Orban said I should get rid of nonparametric Bayesian from the title because he says people use it as a tag to say, okay, I don't have to care about that. So yeah, okay, I see some nods. Okay, good. So that may not be the final title. Anyway, and this is some stuff I did with the postdoc Homo and of course Stephen. So. Okay, so this is going to be kind of a tough talk because there's a lot of background material that I don't think I can adequately cover, namely the GP LVM and the infinite Gaussian Mixture model. So I'm going to have to sort of just give you the equations and the feeling of it, and I can't really go into depth of every part of this model, unfortunately. And at the end, I'm going to sort of try to contrast this with sort of the frequentist thing, a view as I see it, and I want some feedback on that part. Okay, so what really got me going on this was going to NIPS and seeing all these models that we're trying to do like manifold learning, that the first step in their manifold learning would be to draw a nearest neighbors graph. And then this would be the basis of all the rest of their algorithm. And I always thought this was kind of perverse because it seems like the original topology of the space that you're in is like the last thing you want to use, right? Like the whole point of learning a manifold or something is that you don't trust the manifold that you're in originally. And I had this sort of like toy example that I thought I could solve better than these methods, where maybe I have some data like this. And if I were to draw, and let's say these are unlabeled points actually. So, you know, just, we don't know what label these are. But the point is that, like some semi-supervised algorithm should probably fill in, you know, zeros along this part and x's along this part. But if we started with the nearest neighbors graph, and we ended up connecting these guys, then there's really no way to recover from that in general. I know that there's like some sophisticated methods that don't necessarily have this problem, but I was hoping to find some method that didn't rely on this really gross step I thought of sort of discretizing your space and enforcing this nearest neighbors graph that you never came back to. So I thought, and I also, there's this existing problem with clustering methods where they actually, most of them, at least the infinite Gaussian mixture model requires that every cluster is Gaussian, which is kind of an annoying assumption because if your clusters are like heavy-tailed or something like that, then you can't really do a good job of modeling this, or at least in terms of the clusters that you find, they won't really correspond to the clusters in the data. Okay, so that's the problem that we're trying to solve. And now I have to introduce, just for notation's sake, the simple Gaussian mixture model, right? So we're just going to have some sum of Gaussians, and if we put this conjugate prior on it, the normal inverse Wishart prior, then this has the nice property that we're going to use later on, that if we know all the points that are in a cluster, we can exactly integrate out the mean and covariance of these clusters, which is a pretty nice property.
Good question. Can you not approximate any arbitrary shape by just having enough cluster, enough Gaussian components?
Yeah, exactly. So that's a good point. So the Gaussian mixture model might be a good density model in general, but in terms of clustering, it'll, like for instance here we have I think the number of components observed is 20 here, and this is actually like a 2D projection of a 3D density that's a spiral. And probably you might say, well actually there's only really one cluster here, right? There's this spiral shaped density thing. And this 20 doesn't really have anything to do with anything, right? Like that's not breaking up you're going to have to artificially break up your data into these clusters in order to model it well using this model. But I agree with you that it is a consistent model in some sense. The density, speaking from a point of view of density.
So when you say this is one cluster, you mean because it's connected, or because it's a simple shape, or?
I mean because it's connected. That's the thing, that is, the cluster is not really well defined here yet. So, anyway. Okay, so pressing on. Okay, and something that Carl did a long time, or about 10 years ago, was he just put a Dirichlet process prior on the number of clusters, or cluster weights. And then this leads to an algorithm that lets you infer the number of clusters automatically. And you can use the fact that you can integrate out the, well, there's a bunch of different ways you can do sampling, but in the nicest way is you sample the cluster assignments, and then you integrate out the Gaussian parameters given those cluster assignments. Anyway, so this is nice, but as I just mentioned, it has these pathologies where, from a point of view of clustering, it's maybe not appropriate. Alright, so now I have to introduce, this is like the hardest part of the talk, the Gaussian process latent variable model. So can I first ask, like, who has messed around with this or played with it or anything? Okay. So, the basic idea is that we're going to define a smooth mapping from some latent space x to some observed space y. So we've seen y, and now we're going to have to figure out what latent coordinates can be smoothly mapped to get the y's that I observed. And typically, the latent coordinates can live in a different dimensional space than the observed coordinates. So that's what I said. Okay, so it's kind of a complicated construction where we have a different Gaussian process mapping every dimension of, or mapping the x's to every separate dimension of y. But the nice thing about the GPLVM is that you can actually write down the likelihood in a really simple form, which kind of just looks like a big Gaussian. And this, of course, is the kernel, the inverse kernel matrix.
Why is there no x on the right hand side?
Oh, so that goes in, so that, this is k of x. So that's where the x appears. So, good question. So there's one detail in it that was introduced in the first paper where they said, well, we have to sort of constrain the x's if we're learning them to not just sort of go anywhere in the space. So they put this regularizer on the latent coordinates, which will become important later. But also, all it basically does is makes them stay in some nice region of the space. I mean, like, since only the distances between the x's matter, like the whole model, unless you add this part, is translation invariant, and I think scale invariant.
It looks scale sensitive this way.
Yeah, but then if you change the kernel hyperparameters, then it would become, like if you're learning the kernel hyperparameters as well, then the whole thing I think becomes scale insensitive. So, anyway. Okay.
And you're using the same kernel for all the y dimensions, or?
Yeah, so you don't have to, but in practice we do, and in practice we use a Gaussian kernel. Like, this is a place where we could put some sort of more modeling knowledge and more sophistication in, but for the first pass we just use the same, we use isotropic Gaussian covariance everywhere. Okay, so this is sort of me just trying to give you guys a handle on the GPLVM without spending way too much time on it. So yeah, we can say it's a smooth mapping from one space to another, and usually what people do is they have some y that's high dimensional or difficult to deal with in some way, so then they run GPLVM, maximize for the location of the latent coordinates, and then they have some low dimensional coordinates that they can use for visualization or whatever they want to do. And Radford Neal sort of made a cottage industry of replacing every linear transformation with a GPLVM, and he has like 10 papers where, so like, you know, mixture factor analyzers becomes a nice model in this, well actually I shouldn't say that. Anyway.
So is that Radford Neal or Neil Lawrence?
I meant to say Neil Lawrence.
Okay.
Yeah. Right here. Anyway, and there's kind of this nice property of the GPLVM, which is that typically the dimensionality of the latent space is fixed. And then it has this nice property that every extra dimension of y that you observe sort of gives you more information. And he sort of says that, like, you know, the cursor dimensionality is kind of weird, right? Because every dimension that you get should make the problem easier, in some sense, than harder, right? Anyway, so this is kind of like a different way of viewing the modeling problem than usual. But anyway, so the sort of the new part in this work is that you can, since it's warping every point of x implicitly to a point in y, and we put this density, this Gaussian density in x, then we actually are implicitly warping this density into the y space. And the GPLVM is not usually viewed as a density model, but it can be actually. But then it, you know, originally, if you're optimizing the x's, this is kind of becomes, has some problems, but we're going to integrate outer x's, and then we can see that the GPLVM is actually a density model. Okay, so now we have enough modeling tools in our kit. We can to generate some non-Gaussian densities in our observed space. In fact, we can generate non-Gaussian mixture models. Alright, so now I'm going to define the actual infinite warped mixture model. So this is like a really simple thing, right? This whole paper seems like really low-hanging fruit to me, because all we really did was we took the GPLVM, treated it in a really Bayesian way, and then replaced this this simple isotropic Gaussian with an infinite mission model. Like that's it, period, that's the whole model. We can also view this as an extension of the infinite Gaussian Mixture model where we've actually worked it by GPLVM. Right? These are both two special cases. And it's actually like a pretty simple model, right? We just have these two parts of likelihood. We say that the x's should have high density under the latent Gaussian Mixture model, and the warping from those x's to the observed y's should be smooth. So when we're doing inference, there's going to be these two things that are sort of constraining us. We have to have high density under some Gaussian Mixture model, and we have to have some smooth warping to the observed space. And I'm going to make this all concrete later on.
What do you mean by warping?
So by warping, I mean that this likelihood function is implicitly integrating over a space of functions defined by a Gaussian process on each dimension of y.
But so the warping is the mapping from the manifold to the observation space, no?
Yeah, it is.
So that's another way to think of it, so you can think of dimensionality reduction.
Okay. All right, and now this is going to be the last hump of math before we get to some more interpretable things. Okay, so I don't know if this is really that illuminating, but we can view this as a generative model, where first we take a mixture model. For each mixture component, we just independently choose a Gaussian. Now we have a mixture of Gaussians. And then for each dimension, we're just going to define some warping. And of course, you can't really draw a function. This is kind of misleading. And now for every observation, we're just going to assign it to one of the clusters, draw from that Gaussian, and then look up how to warp that point to the observed space. So, all right. So now the abstraction is over. And here is me just starting from some fixed mixture of Gaussians. This is like very early on in the project. We just, actually like the day we thought of this model, we sat down and just coded up this simple warping code where we wrote down a mixture of two Gaussians, and then we just randomly sample y's, which define warping. And then we actually also warped the density, which you can't really do in closed form, but we tried anyways, to plot how the whole Gaussian was warped into the observed space. So, and in this case, these two spaces have the same dimension, but there's no requirement for them to have the same dimension at all. Okay, so this is just like a few draws, and I mean the only question you can ask is, do these look like data that I would expect to see in the world, right? That's sort of like the only evaluation you can make of the model at this point. And this is like a sanity check to make sure that this model actually does something sort of sensible. And I would say, yeah, it looks like it does something sort of sensible, right? I mean, I don't know how often you guys have actually stared at scatter plots of real data. You know, all I'm trying to say is it looks reasonable, and this is sort of an illustration of what the model is doing. It's warping the Gaussian Mixture model. This is the latent space. This is the observed space. So, any questions at this point?
So in the warped space, the measure changes by the Jacobian of the transformation. Is that hard to take account of?
No. I mean, there's a way that you can warp or sample from the posterior without actually computing the Jacobian. But if you I mean, the measure is kind of weird, right? Because it can be some like weird overlapping thing anyways. So actually computing the density in this space in closed form is not tractable, and we have to do it by sampling. So there's this possibility, there's this thing called GPLVM with back constraints that enforces that the warping from this space to this space is smooth. But we're not using that here. This is just like a very simple vanilla implementation of this model.
So that means the plots you're showing, how do you get the density there? Is that just the kernel density estimate, or?
No. So this is like, yeah, day one. This is all I did was I took the points that define these ellipses and warped them, conditioned on these points having been warped to the spaces that they were warped. So.
Okay.
Yeah. And I mean this is not quite an accurate rendition, right? Like you can see that they kind of overlap themselves. Anyway, it's just the first attempt at visualizing. All right. So. One thing that we kind of have to worry about in this model is actually doing inference, which actually turns out to be not so hard, because we know that once we have the latent coordinates, then we can, sorry, I guess I should say, once we have the latent assignments, we can update the latent coordinates using Hamiltonian Monte Carlo. And then once we have the latent coordinates, we can update the cluster assignments by gate sampling. And I always feel like every NP-based paper spends like way too long talking about inference, because when it's just something mechanical, right? This is like the whole thing about the equation, right? You write down your model, then spend a while trying to be clever doing inference, but it's really not the heart of the matter, right? This is just how we get from our prior and left pivot to our posterior. And all the hyperparameters can kind of be set empirically except for the concentration parameter of the Dirichlet process mixture model. So, well, maybe I should say we never used cross-validation, we just set it to some reasonable value. But the problem with this inference method is that Hamiltonian Monte Carlo actually has a few parameters that you need, like step sizes, that there's no real principled way to set. So we had to fiddle around with that. But actually, Hamiltonian Monte Carlo looks really pretty. And okay, so this is using Hamiltonian Monte Carlo for a few steps to update the latent coordinates, and then this is the observed coordinates. So this is y, this is x, this is the latent Gaussian mixture model, and this is the an attempted rendering of the I guess class conditional density in the observed space for this toy data set. And yeah, I don't know. I kind of like that everything has a sort of an interpretable place in this model so far.
But this data set, you could have figured also with a single Gaussian, right? So the standard GPLVM should have been enough for this data set on the left, no?
Yeah, exactly. So I started off this model with 2 Gaussians, and after you run inference for long enough, then it'll be modeled at 1 Gaussian. Yeah, so this is just from the start of inference. Okay. But that's a good point that I'm going to return to. Okay, we will stop this. Okay, that was the demo. Okay, and there's this nice thing that the fact that we allow different numbers of clusters actually helps us to mix during inference. So here's a spiral data set where we're looking at the latent coordinates here, and we initialize them to be the same as the observed coordinates because we don't know how to initialize them. And we say, okay, also there's 1 Gaussian that's describing them. And here's a few examples of a few snapshots of the sampler. And what it does at first actually is it adds a whole bunch of extra latent factors, or latent Gaussians, and then over time it sort of merges them back together again, and recovers this appropriate 2 latent Gaussian posterior, or example of that. Anyway. Okay, so this is actually running our method on some toy examples. And I mean, there's a few takeaways here that I want to get into later, but the main one is that you can see that it kind of works pretty well, right? And these are all Gaussian, or all data sets for which in the observed space, a mixture of Gaussians would have to just sort of tile it with a whole bunch of tiny Gaussians. There's not really any good way to model these with the naive mixture of Gaussians. And also the number of clusters being recovered is kind of seems appropriate. Right?
But if you did the density-based clustering, you will recover all this, right?
What do you mean by density-based clustering?
Where the clustering just tries to follow regions of high density.
Maybe. I mean, the thing is that also so these are unlabeled. There's no class information in this data, but it still is grouping the the different arms of the spiral, for instance.
Yeah, but personally I cannot believe that because
and they're connected according to your definition of cluster before.
Yeah. So that is a good point. Yeah.
Because whenever I see those sort of things, it makes me feel that if it's a clustering problem, I believe even a human cannot say what a cluster is there. And so if we say these are clusters, that means we sort of tune our algorithm to say these are clusters.
So that's a good point, right? We should really define exactly what we're going for here and what we mean by cluster before I can say that these results are good. This criticism well taken.
Dave, I have a question with respect to the second one. I mean, how is it? Is the circle sort of closed? I mean, topologically, it seems to me a bit difficult to imagine how the mapping is prepared.
I don't know if you can see this, but actually what's going on is that there's 1 Gaussian that's being stretched around, and the end of one side is right here. I don't know if you can see this sort of thing sticking out.
Okay, yeah.
And it's actually, well, I don't know if you can even see it, but yeah. So it's actually approximating a circle by a line that's bent around.
Okay.
Yeah. Anyway. Okay, and now we can kind of compare it to the GPLVM in terms of the interpretability of the latent coordinates. And this is, again, just a toy example. This is the GPLVM maximizing the latent coordinates. I don't know what happened there. This is the infinite warped mixture model. Oh yeah, and by the way, this is the observed data for this figure is the 2 spiral data set. So maybe think in your head what would be an appropriate Bigman writing of this. I don't know. And all we're just saying is that this seems like a pretty good latent visualization, right? We're saying there's actually two lines, it's only happened to them to be warped, but really these guys are sort of connected to these guys, and these guys are connected to these guys, but the lines aren't connected at all. This is just our model enforcing that there's one latent cluster, and it does a pretty good job, but it just says that all the points have to lie on one line instead. Right? This is just to demonstrate that you can use this for visualization if you want. Okay, and this is just one last spot where I actually sort of tried to answer your question. This is me running just an example from the posterior of a spiral data set given only one latent cluster. So we're warping one Gaussian into this this data set where every circle, well, basically every point is a data point. And actually, you can warp a single Gaussian to have these sort of ridges of high density as well. And so, yeah, the GPLVM originally, if you use it in this manner, is actually a pretty flexible density model. So. Okay, but then here's sort of like a pathology, right? Here's again the spiral data set, and here's us actually doing a good job of plotting the posterior density in the observed space. And this is where we allow the number of clusters to be more than one. Here's where we force the number of clusters to be one. And you can see there's sort of like, this model can't help but putting a bunch of mass between the different regions of high density. So. Alright. And we have a table with numbers on bold at the bottom, but to be honest, I don't think we really did a very serious evaluation of this this model. I mean, we're using UCI and some toy data sets. Yeah, it's in this paper. Alright, I just want to talk about a few limitations of this model. So one of the main ones is that it sort of has a single scale for everything, and this, and not just every dimension, but within the space, the clusters all kind of have to be roughly the same size because the kernel is isotropic. So this is an example where this outer circle was able to be sort of unrolled, but the inner circle, you can see that in the latent space, it's just being modeled by a Gaussian that's just sitting there. It's not being unrolled at all. And the model's not really going to care much about this cluster because it doesn't have to explain very much variance compared to this data set. The other main difficulty is obviously that we just did everything naively in terms of the GPs. So it's n cubed, so the amount of data we can use is limited to like, a few hundred or maybe 1,000 data points at most. So. Okay, yeah, so the future work is just better inference scheme, and we can probably make things run a lot faster if we really try. Hopefully this can actually be used for semi-supervised learning like in that original plot that I showed. That was the original motivation. We can have like a fancier density model, right? We can use hierarchical density model, or hierarchical clustering if we wanted. And yeah, it'd be also nice to have an actual application of this instead of just this sort of like toy UCI stuff. Yeah. Okay, so now this is where I'm really happy that I got to give this talk to this group because I really want to see what your impression of like this whole recipe is, right? So yeah, we actually did do this, right? We actually sort of started thinking what would be the generative model. We wrote up some simple code to make some examples. Then we spent a long time writing the sampler and sort of fiddling with it and trying to, like there was a bunch of different ways we could have done inference, and we tried a few of them before we hit upon this scheme that worked pretty well. There's this whole thing where, the modeling sophistication I think in general is like way ahead of inference sophistication. So right now it's easy to write down really powerful models, and I think it's probably like another 10 years before we can use these on like more than 1,000 data points for most applications. The cool thing though is that like the modeling decisions are sort of in principle separate from the inference scheme, right? So once I came up with the model, the rest was just sort of like, perfect grad student work, right? Like work out all the details. But these details sort of don't necessarily affect your answer if you're doing things right? So there's not all this like ad hoc, like now I apply this test, and then I apply this algorithm, blah, 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 that would affect your answer. Right? The idea is that if you run your chain long enough, it doesn't matter how you do inference. So, all right, that's the end.
So I missed how you actually decided to put 2 clusters, 3 clusters, or whatever.
Oh, okay. So in the Dirichlet process mixture model, there's there's when you sample the new cluster assignments, there's a chance that for every point you'll sample a new cluster that no one belongs to. So, and also sometimes you might have a cluster who who belongs to him gets reassigned to other clusters, and then that cluster sort of disappears. Oh, Dominic?
As motivation, you mentioned heavy-tailed distributions. I was wondering if you want to generate a heavy-tail distribution from a Gaussian, then you need a function that gets infinitely steep, right?
Oh, that might be a good point. Yeah. Yeah, I see what you're saying. That really the warping function would not really be that smooth. No, that's actually a really good point.
But can you generate a heavy tail distribution from a mixture of Gaussians?
Yeah, but I mean, he wants to assign the clusters by the mixture components, right?
So that's actually a really good point, because we put that motivation in there, but none of our examples really dealt with it, and that's actually a really good point. Yeah. Thank you.
So coming back to this problem of what is a cluster and so on. So I think it's tricky to talk about non-parametric approaches to clustering. But maybe one other way to think of it is as a non-parametric density model. And then one can rephrase. So we once tried we did some work on this where we rephrased the clustering problem as saying it's a non-parametric density estimating problem where you want to decompose a density into components that can be distinguished. And one way to measure it is that you can do two-sample testing between components. So you just want to decompose some complex density into a sum of simpler ones, such that the simple ones are pairwise distinguishable. One way to do this, you can do this in a non-parametric way also by embedding in the physical hidden space. And I mean, I'm not saying we found a good solution, but somehow for me it was illuminating to think of it as a non-parametric mixture or density estimation problem.
That's interesting.
But what do you mean by this dimension? So
for instance,
you want it as a sum of two.
So you have a density, you want to decompose it into simpler in some sense. In simple you can have a prior or a regularizer into simpler components which are distinguishable.
Okay.
So for instance, it's interesting to think about what is suppose you observe a superposition of a Laplacian and a Gaussian. So a standard clustering in the intuitive sense would just say that's one cluster, but maybe there's a meaningful way in which one could ask for a non-parametric clustering algorithm to separate this into a Gaussian and a Laplacian. Because somehow a Gaussian and a Laplacian are both simpler than a mixture of Gaussian and Laplacian, according to the right kind of prior. Maybe.
Yeah, I guess there's nothing in this model that's trying to make the models be or the observed clusters be separable. It's just that by trying to not put extra mass in other places, we end up sort of just by accident making them hopefully separable. But they could overlap, and that's fine.
So can I ask two big questions? I mean, one question relates to what Dominic was asking. Is instead of a cluster being just in the latent model a single Gaussian, right? Could you have it as a mixture of Gaussian centered at the same point?
Right. Yeah.
And would that
I mean,
is that something that the rest of the model can carry through easily?
Right. But if I was going to do that, I would just make the latent cluster be like a T or some infinite mixture of Gaussians at a single point, because that's presumably what you would be wanting to do anyways.
You mean infinite mixture of Gaussians at a single point,
Yeah.
centered at the same place?
Yeah, just in the sense that like a T or any most heavy tail things can be.
By GMM, yeah.
Yeah.
So, but is that something that you can? Is that a simple extension of your?
It is if we can. I mean, the inference might be harder because we might not be able to integrate out in closed form the mean and covariances of all these T distributions. We might be able to. I haven't really thought about it.
Okay. So the next question is inference on inference. So you say it takes O of n cube or something?
Yeah, per set.
And what could you? So you say maybe we can make this better, but I have no sense in how much the n cube can be improved. It seems like it's a problem with this sort of Bayesian models in general, right? And
Right.
so,
So the
what
general
have people been able to do?
Right, so the general
in
answer is that
field?
there's been a lot of work in approximate GP inference, and most of the schemes end up being n times m squared, where m is like some number of pseudo points that you're actually modeling. But the thing is that it's not quite clear when to use which approximation yet. So that's sort of like this big missing piece of the puzzle. So,
But so far nobody has been able to go below n.
well, I mean, if you look at all your data, you're n already, right? So I don't. That's fine with me.
No, I mean, I'm saying, if, say for instance, for regression or for classification, you don't necessarily need to look at all your data for a single feature point.
For a single what?
So let's say I'm doing classification or something.
Oh, okay. Oh, if you're doing like nearest neighbor, then you might have some great data structure that lets you like it only in
Yeah,
subset.
something like
But I mean, to even create that data structure, you really have to pass through the data once. I think.
Yeah, but that's that could be viewed as an offline thing that you do, and prediction is online thing.
Okay.
And so.
Well, I'm still worried about going from n cubed to m, so better than n is like far in the future for me.
Okay.
One point that I didn't quite get. So the nice thing about the Gaussian Mixture model is that you can integrate it out analytically,
Yes.
and the GP is also something you can integrate out. So, and you said you can also integrate out the combination of both?
Only when we sample the latent cluster assignments and the latent position. I mean, that's the part that there's no closed form way to integrate over.
Okay, thanks.
So,
So have you generated a few more samples from the prior?
No.
So just the actual prior, not at all.
no, I mean, it's kind of a weird thing too, right? Because you have to, yeah, we could, but we never did, yeah. So the question is, so the question is, what if you would use an IVP instead of a DP? But I actually don't know what the different like features of the IVP, like the different columns would correspond to.